Zhongqi got his bachelor degree and master degree from the University of Minnesota, Twin City, in the ECE department, and he joined in the UH ECE department at 2024, and this is his 5th year, and his PhD topic is hybrid quantum classical optimization for data center energy systems. Thanks you, all of you.
Since it's already recorded, let's start it. Okay, welcome everybody here to join my PhD defense. And my topic is the hybrid quantum classical optimization for data center energy systems. Okay, and then we'll start with the next slide. Okay. So here's the outline. At the beginning, we will start the introduction with the background of mixed integer linear programming and quantum computing. Then we will work through 3 works of mine, and then we'll draw the conclusion and future works. Okay, so what is the mixed integer linear programming? So mixed integer programming is widely applied in a lot of applications. For example, in production demand, in route planning, like also the energy management and the LM task scheduling. Yeah. So because it contains 2 kinds of variables. First one is a discrete variable. We can rename it as a state. Okay, either state 1, 2, 3 is a discrete variables, and also amplitude. Amplitude means it's a continuous variable. It's a feeling of levels. It's a feeling of levels. Like it can be 25, 33, or something in the middle. It can be anything. So that's why we focus on this one. This one is really really interesting, and then we focus on the quantum computing. The quantum computing it has 3 steps. Basically, it can explore a lot of explore the multi-dimensional spaces in very large problems. Okay, so then we can trans the solution back to we can use and understand. For those problems, the classical computer is really hard to solve the problems. Basically, we can make it to 3 steps. First one, the quantum computer will activate the state, which is to do the initialization, put every state everything in entanglement with the equal possibilities. Then the quantum computer will encode the problem into itself. Then it will unleash the power, which let the ball drops, and then the quantum computer will get a solution from the minimum state. Okay. In academic conclusion is it harness the principle of quantum mechanics, superposition, entanglements, and interference to process information in parallel and probabilistic ways, enabling solution to complex problems. Okay, let's do a quick toy example to illustrate why the quantum computing is fascinating. Okay, so imagine in my hand there's a mystery coin, and you do not know if in normal there should be a tail and the faces, right? So, however, you do not know what the coin has. It could be both faces or one tail and one face. So in classical computing, you're gonna inquire 2 times. First time you're gonna ask me, well, show the face of the coin, and then flip over and inquire 1 more time. Show the tail to see what the picture is. If the picture on both sides they're the same, it's the balanced. It is a constant coin, which means they share the same traits. And if the tail and the head is different, so it's a balanced coin. However, in quantum computing, we can just achieve this one in one single query, which is we can mix up with the state with an entanglement 0 and 1. Then after this inquiry, we can distinguish the outcome by the final solution. it's either zero. If zero is a constant coin, which means both head and tail they have same pictures. If this one is balanced, which means they're different. So basically, we can shrink the size. We can shrink the query times. So what's the advantage between what advantage of the quantum computing to the cloud computing? Usually for cloud computing we refer to the CPU, the central processing unit. So in CPU, the good thing is it's a versatility to a lot of the classical algorithms, right? And however, the defense for the central processing unit is limited parallelism, right? That's why we invented GPU In some of cases, it can be run really slower. For the QPU, thanks to the quantum tunneling and parallelism, we can do parallelism. We can do multiple inquiry in a single time. And for the tunneling, which means it will have less opportunity to stuck into the local minimum. We will look into that one later. Okay. However, for the QPU, because it merged technology, it's kind of limited in special cases. However, in those cases, the quantum computing already show its advantage. And in the quantum computing, there are two mainstream technologies. One is the quantum annealing. The second one is digital quantum circuit. The quantum annealing is inspired by the classical annealing, and for the digital quantum circuit, it's inspired by the digital circuits. Okay, well, take a look into these two ways. First one is the digital quantum circuits. For this one, the leading company is the IBM. IBM is already fabricated chips with 433 qubits. And it can solve both continuous and discrete problems for now, based on the papers that already published. And for quantum annealing, although it can only do the discrete problems, however, it has more qubits than the digital quantum computer has. For now, it has 5760 qubits, so it was way more than the digital quantum circuits. Okay, so if we draw the conclusion for both two ways, we can use a metaphor that makes the digital quantum circuit as a spaceship. Okay, the spaceship carry a lot of devices, can do a lot of things. However, it's need human operations to explore the planet or explore the universe. So which means it could be universal, but it kind of for now the performance is not guaranteed because you need to do a lot of operations. However, for the quantum annealing, it's more like a microwave anisotropic probes. For this one, it can measure the cosmetic background microwaves. Although it is it's not very universal. It can only do the discrete problem. However, it can give you a great picture because it has more qubits. We can see the local. You can see the minimum of the minimum temperature of the space, right? And can do it by one shot. So that's why we choose the quantum annealing as the main computing solver. So and we choose the D-Wave as our computing platform. First one for the D-Wave quantum annealing, it has 3 steps as we illustrated before. First one is the initial qubits, which position the qubit position at 0 and 1s. Then we coupled the every qubits with the problems that we want to solve. Then we let the ball drops, and the magnetic field once we plug the magnetic field, the state will changes, the state of energy will change, and you will have higher probability to observe the solution of the lowest state. Okay, in the mathematical way is that first one we do initialization. We put the initial Hamiltonian as a we represent everything in easy model. And the first step we put the initial Hamiltonian, which is the initialization. Okay, and then we set the problems, which is we put the final Hamiltonian into the problems. And then third time, we unleash the power. First, thanks to the Turing effect, it won't go to the classical path, but the quantum path. We can go through the barrier. Okay. So it will unlikely to stuck into the local minimum. Okay, and then we can draw the conclusion that in the quantum annealing in D wave. Okay, first one we have the problems. Then we encode our problem into an Ising model. Then we put the Ising model to the D-wave quantum annealer. Then we get a solution. Okay. Good. So let's go to the work one. So in the work one, the motivation is the AQC band for MLP and its software. The motivation of this work is internet data centers, energy management, because for now, in 2020, the data center worldwide already consume 200 to 250 terawatt hours. That's a great amount. Is roughly the same as the power consumption, energy consumption in South Africa. That's a great amount of energy. And inside the data centers, it's very complicated because you have a lot of renewable energy resource inputs, and also you have a lot of devices that you need to control, and therefore it's a very good example to show the application of the MILP, the mixed integer linear programming, and how the quantum computing do. Okay, so inside the IDC, the Internet Data Center, so we have two kinds of variables. First one is the binary variables. Second one is continuous variables. In the binary variables, that we have the switches. We have the switch of all the devices like the chiller generators, a condensed tower, also the lights, right? Also in the battery, we have two modes: discharging or charging. So those are the binary variables. For the rest of for the continuous variable, we have temperatures, we have the energy we bought from the outer grid, we have the temperature control for the heating, ventilation, and air conditioning systems, and also we need to control how much power or energy we need to discharge or charge from the batteries. Okay, then this is a generalization of the problem, which is the MILP. The MILP is mostly NP hard, which means it cannot be solved in the polynomial time until we prove that like P equals to NP, right? So then we can regard it as a very hard problem hard problems if the scale goes large. For now, we have three methods to deal with kind of problems. The first one is the iterative method, which is go through the possible solution one by one, and to see what the objective is, and however, this one is pretty computation expensive, right? And then we have a branch and bound, and cutting plane method. In my work, we choose the cutting plane method as the target algorithm to find this final solutions. For the cutting plane method, one of the well-known algorithm is the Bender's decomposition. This is one proposed in 1972. And now we already have a lot of updated version for Bender decompositions, and this one is one of the classical Bender decompositions. So this is on the left is the algorithms. On the right is the workflow. Basically, we're going to divide our problem into two set of problems. First one is the master problems. The master problem, in our work, master problems contains only binary variables and one continuous variable lambda that connects to the subproblems. And then for the rest of continuous variable, it goes to the subproblems. And the visualization is the iterative method, which means once the master problem has its binary solution, it'll pass the binary solution to the subproblems. And once subproblem gets solved itself, it'll pass the feasibility and the optimality cuts back to the master problem to refine it. Basically, shrink the feasible region, until it reaches the optimal. Okay, in our algorithm, we can set a tolerance bound, upper bound, to see bound to, which means it is a sign for stop. So it's a sign to stop. Once the upper bound and lower bound of the connection variable it was within a tau, which is tolerance, we can make it stop and recognize as the final solution we want to use.
I'm sorry. Oh, sorry. I wanted to clarify before you went further because I'm confused about something. So T, A, and G. Can you just briefly walk me through what those matrices are?
This one
specifically T, A, and G. Yeah.
Yes. So for the T in here, the X is the discrete variable and Y is the continuous variable.
Got that.
Yes. Then we move, since the X is a discrete variable, we can move that to the master problem because this one in this constraint only contain the discrete variable that we want to keep it into the master problem because this is the one. They have the same variables, same kind of variables. For the rest of continuous variable, it goes to the subproblems.
Yeah, but I mean so those are coefficients for a linear system.
Yes.
Right. I don't understand how those relate to your problem.
Yes, I will.
Okay. I think for the different engineering problem, this T and P are kind of a constant something, not a control variable. But usually depending on the physics, for example, power system, Kirchhoff's law, all these type of things. So this is here is just a kind of
coefficient
high level framework.
Okay.
And then later, okay, for the engineering problem, we will define the T.
Gotcha.
Yes.
So
Okay.
right now they are just some matrices of coefficients that we know. Okay.
Cool. Then, based on the classical Bendel conditions, we propose our HQC band, which is a hybrid quantum classical Bendel conditions for mixed interior linear programming. So, basically, in the large scale pictures, in the greater picture, we basically we refine the master problems of the Bendel condition from the previous representation to a quantum representation. We change our connection variable by discretized the continuous variable into a binary representation with a certain tolerance. Okay. And then for the feasibility cuts and optimal cuts, we can add it back to the objective function with a penalty pk and pj, and these are the quantum representation of the constraints. Okay, right? I made detailed derivation in my proposal presentations, so we won't go over that one in the final work. So this is the algorithm that we use, and this is a great picture. Basically, for quantum computers, it solves the master problems it passed the integer variables to subproblems, and since then we use the classical computers to solve the subproblems and feed back the feasibility cuts and optimality cuts back to master problem and make the iteration. Okay, and finally we will get the solution. Okay, then we say, okay, why don't we why don't we contribute to our open source communities? Like, then we put our work as a Python package to the GitHub, and so are open sourced. And so this is the structure or the outline of our algorithms. It has 3 or 4 parts. First one, we get this target problem we want to solve. It's a growing model, and then we can let user define what kind of problem, what kind of model they want to use. Once they solve the once the model gets a solution, which is a math problem, it will check by the threshold functions, and then goes to subproblems. In subproblem, we have two approach to get the cuts back to the master problems. We will goes into detail now. First is the processing of the target model. Okay, in the target model, once we get the Groby model, our Python package will automatically do the pre-processing, divide those coefficient matrices or the vectors into two sets. One set is for master problem building. The other one is for the subproblem building. Okay, and then then is the master problem solving. In master problem solving, we offer 3 ways. 3 way of models. First one is the classical Groby solver, which is computed by the CPUs. For also the simulated quantum annealing provided by OpenJFJ solver. This one is a Japanese company, and for those 2 methods, is computed by CPU. However, for the second one, it's using CPU to do simulate quantum annealing. Okay, if you do not have the access to the quantum computer, you can use that to mimic the process of quantum computing. And for the GPU one, we have the simulated bifurcation. This one is another way. To do the simulated quantum annealing. However, this one is using GPU. So GPUs as the computing platform. Then come with the quantum D-wave quantum annealing service. Okay, and we offer three methods for the D-wave quantum quantum service. If you have the access to it, the third one is the hybrid mode, which using the hybrid solver service schemes of the D-wave. The second one is the D-wave. This one is offered by the D-wave quantum service. The D-wave quantum service. This one is using the quantum module directly. So for the hybrid quantum service scheme, here is the scheme. First, it will go to the classical heuristic method. Then it pass the solution to the quantum module. If it's not good enough, go back to the heuristic model and go to the quantum model. It will do iterations, and then once it passed the threshold, it will give you a solution. The third one is the cut adding techniques. And here we offer the user two options. The first one is the normal method. The second one is the L-shaped method. So this is the workflow of both normal method and the L-shaped method. So once we receive the option from the user, we will go. If it's normal, it will goes to the door of the subproblem and get a solution. Get the optimality cuts or the feasibility cuts. if this choose the L, do the L shape. First, we will do a pre-check. If the object function of the L sub is equal to 0, it will go to the D sub, then it will add the arithmetic cuts to the master problems. If it's not, it will create a new the dual problem of this L-shaped subproblems and feedback the feasibility cuts to the master problems. Then after that, here's our algorithm conclusion, and here on the left is the example Python code. Once you build the model, you only need 2 lines of code to it will automatically run the solution for you, and during the computing process, it will give you the text output to inform you what is going on right now. It tells you, okay, what's the cut we're adding, and what's the wrong we're at now, and what's current objective, what's the current upper bound and lower bound of connection variable, what's the gap between it, and what is the absolute gap between it. So those meta information is stored in the JSON file in the folder. Yeah. So once we have these tools, we can use this chef to cut the problem, right? So then this is my second work. Okay, this one is a little bit weird. Okay, so in the HQC bin here, we can see in the data center we have a lot of devices, and we have a lot of devices. So we have the solar panel, we have the batteries, we have the auto grid, the ventilation system, the IT services, the light. Okay, and so here we want to minimize the total cost of electricity imported from grid. So what devices consume the power? The HVAC system, the heat, ventilation, air conditioning system, the IT rack, the computer system, the battery charges or discharges, and the solar input, right? The solar input is negative because we use an injection. We don't need to buy from the grid, right? So in the HVAC system, we have the supply, the ventilation, chiller, pumps, condensed tower, and for the battery system, this is the equation. We have in the charging, we have the coefficient for charging and discharging, because you have some everything is not ideal. With the charging, there will be some loss, power transmission loss. Okay. For the rest of this is the battery static requirements, and this is the battery state at every time. Which means for the battery charging is like you need to have an upper bound or lower bound. You don't want to overcharge, and you don't want to consume all the energy from the battery, because if the battery below to 10 or 20, it will hurt the batteries. That's why the iPhone has alarm when your battery is low, either 10 or 20. So then come with the temperature. For the temperature, this is the temperature bound for the room temperature, because in the data centers, since you have those computing nodes, you don't want to temperature get too high or too cold, right? And that will if you go too cold, there will become condensed water that will hurt the device. If it's too hot, the heating really hard to it will cause fire, right? And here is the ventilation requirements, and this one is we need to calculate the minimum capacity of chiller and condensed water we need to use to do the heat exchanging. And here is the upper bound, lower bound of AC temperature. AC temperatures. Here for this one is the total heat that we need to extract from inside to the outside, right? And for this one, for these two, it's the amount of chiller condensed water we need to take away the heat. Okay, and that one is once we calculate how much heat we need to extract from the inside, we can compute the energy consumption of chiller and condensed tower, and we can compute the energy consumption of pumps in condensed towers, right? And for beta, they are the coefficients. Similar, we can compute the energy consumption for ventilation, return airflow, and we also have ventilation requirements. Those betas, for the beta, they're the coefficient, and for the continuous variable, we mark them in this color, and for the binary variables, we mark them with this color. Therefore, our problem can be generalized as a mixed integer linear program, MLP here. Then we used our tools, the chef, our tools, which is QC band, to solve the MLP. Okay. This is the solution we get. The first one, we need to do the comparison of the solver access time. Okay, so we compare the master problem solving time only, because for subproblems they are the same. Okay, they are all computed by the classical computer. So I don't think it's necessary to compare that part. Therefore, only compare the master problem solving time. So for the classical computer, we can see at the beginning it consumes less time than the quantum computer quantum computers. Then it will go up. For the quantum computer, it relatively has same solving time. Okay, if you look the result in another way, which is cumulative solver access time, we can see that okay, the classical computer will consume about 20 seconds to solve the problems, to solve the master problems, and for the quantum computer, we use way less time. Even though for the one cut method, it use more iteration than the classical computation. However, the total cumulative solver accessing time is way less than the classical computer. However, then if we increase the cut per iteration, you will see that okay, now the time goes much less than the classical computer with less iteration. In terms of iteration, we can see if we put three cuts every iteration, again we can save about 30% of iterations. And we go to 6, and in average we can save 42. We go to 9 cuts per iteration, we can get 50% save, 30% off of the iteration. Okay, talking about robustness. Okay, for robustness, we can see for our histogram, for our quantum histogram, the solver accessing time is pretty dense. It's range from 0.01 to 0.03, whereas the classical computer range from 0.0 to 0.2. It's widely spread to the x-axis, which if we look into the standard deviation comparison, we can see that the quantum computing, it's like 896 can kind of 96% of the standard deviation, which means it's really robust to any kinds of problems. Therefore, we can conclude that okay, the HQCBN outperforms the classical approach in terms of solving access time, iteration, and robustness. Okay, then come with the last work. So once we in the previous one, we already know how much power the data center, the internet data center consumes. However, recently, thanks to the AI, we're living in the AI region, right? In AI era. A lot of companies, they put those large language model to the internet data center and let it to train it. Okay, we have Gemini, we have Zhao, we have GPT. So according to a report, the training, the energy consumption to train a GPT-3 used 300 megawatts hour. This is a great amount of energy. It's equals to 130 U.S. homes annually energy consumption. This is a great amount of energy. So that emphasized emphasize why the energy management in data center is vital. Okay, so can we make our model more good? Can we make our model better or make more detail? Yes, we can. In the work 3, we only consider a single internet data centers, and in the probably we can make it 2, right? We can let the internet data center communicate with each other. For example, we can, for data center A, probably is busy. Probably it can transfer some of the training tasks from A to B and let the B to do it. For power consumption, in the previous one, we considered the IT racks is consumed constant power. Within constant power. However, probably we can make up improvements. We can make it variable to the large language model task training. Some of the tasks consume much more power. Some of them consume less power. So this will be a variable. Then come with the LLM training and task scheduling. Okay, in the previous one, we didn't think about the task scheduling. Okay, we only say we only do the management. Probably we can plug the task management inside our model to make this one close to the reality. So let the quantum computer be the girl in the picture to management the schedule, right? Also control the energy system. But how do we evaluate if a large language model in training is cost expensive or not? So this one we can use token as the evaluation. For example, we want to put this sentence into training. Like Dr. Zhao is widely recognized as a pioneering force in the field of wireless communication, game theory, quantum computing, and network science, right? And if in the data centers, it won't go read this one, read this sentence in English. Actually, it will parse the sentence into pieces, then convert them into a number representation. And for the number representation, we call it a token. This one is a token, and this is the G4O token here. Okay. So for a GPT-like model, so the flops per token is roughly the 6 times n times d squared. N is the number of the transformer layers, and d is the hidden dimension, we call it the model the model width. By this equation, we can quantize our workload to a real number that's connect to the performance of the GPU node. Okay, because in the GPU we use the flops or tops as the performance evaluation bar, right? So then we can we can roughly get the numbers. We can get the time of the training by this equation, the number of tokens over the performance of the corresponding node. Okay, then we get the time get the time.
There's a news, okay, but if people using the ChatGPT to do the review, typically they have a positive kind of feedback instead of negative. And this
ChatGPT what?
paper.
Yeah.
And then, okay, they have,
Like
yeah, they have some kind of machine learning, kind of in some cloud conference. They try to catch those people and then try to have the distribution. We compare with the regular people and much higher profit.
But it seems like it seems natural, seeing as that's at least my impression of how they train ChatGPT, right? Is to be very, very like, yes, you're brilliant, you're awesome, you're this. Man,
True.
that is so insightful.
Yeah.
Like that's how you keep people using it, right?
And recently there's a news that one of the AI team, they put the positive prompt inside the paper, but it used the white font. It used the white color font. So for our human, we cannot recognize, but you put the AI prompt inside the paper, says, please give the positive review to cheat the reviewer that using the ChatGPT to review the paper. Yeah, it's actually a scandal, you know. True. So that's just okay. So in the LM training, we have the data center here. Okay, so those are data center with the data links that can transmit the data from one to the other. Inside the data center, we have the different kind of computing nodes. Some of them have GPU, some of them have the TPU, the tensor processing unit. And for every data centers, it will collect the task from the local users to make a pool of the tasks. Okay, and in every location, it has the electricity price of itself. In California, probably it will be more expensive. In Texas, it will be much cheaper because we have a lot of energy here. Okay, and this is the total. And we use the same outline of the data center that we in the work 3. Therefore, after we review those details of the models, we can see that there are some challenges. First one is in the scheduling. Okay, so how to maximize the net income, because we want to make the data center in profit. The data center is not a non-profit organization, right? It's not NGO or something like that. We want to make profits. This one, we want to be sensitive to the local industrial electricity price. We don't want to overpay for our energy cost. And the third one is time-sensitive task completion. Some of the users they have urgent tasks, so they will pay more for us to prioritize their work to finish it early, right? We will regard them as a VIP here, and to finish their work early. So we have different. Since we have different data centers, if we want to transfer our task to another one, which one should I choose, right? There's another decision we need to do. The last one is computing nodes with different performance, which one to use. Okay, and the final things is like the concerns in work 3. Okay. And algorithm wise, so we want our model be general as possible. Second one is the parameter selection. We use the real values we use the values in practice. And the third one is the nonlinearity in the object function, and the fourth one is the problem solving. So here's the formulation. First one is our object function. We want to maximize our revenue. Maximize our revenue. The revenue contains the profit that we finish the work. If we for time sensitive a project, if we abort the mission, we need to pay for the user, right? We need to pay for that because we make them down, right? The third one is the transfer cost. We want to transfer to another data center, we need to pay. This one is controlled by the two data variable. First one is confirms of the transfer. This one is the what node that this job used. Okay. The third one is the electricity bill of every locations. So in the task the definition, we have 4 kinds of tasks. First, actually 3 plus 1. First one is done, which means this work is finished. Second one is abort, which means we didn't make it. We have to refund to our user. Third one is the hold, which means if the user does not say it's time sensitive, we can put them further. We can put them in the future, right? Because it's not time sensitive. So for the job case, we'll have the one we are currently working. We have the one with time sensitive and all the other regular jobs. Okay. For the one we're currently working and time sensitive, we cannot put up to the future. For the time insensitive job, we cannot we cannot abort mission because we can put them aside. Why do we need to abort, right? So in those, if then we can do the universal job scheduling here. With this one, for this constraint is universal in every kinds of job, every kinds of tasks. First one is this one. It basically says, okay, if the task is done, it must be done by one of the node. The second one is if the job choose to if this use is the state of running, right? If it's running, if the node is running, the state of the assignment must be 1 because you are already run the job task. The third one is the balance, is the logical relation between the precedent start and shutdown. There are 3 scenarios. First one, if we do the start, we can see the US1 vs US1, and this one is 0. The equation holds. In the middle, 1 and 1, 1 and 1. Those are 0, still holds. If we shut down the tasks, 0, 1, and 1, we can see it still holds. The fourth one is like we cannot start or finish at the same time. The startup shutdown cannot be same time. For the current working job, we'll go through those ones and see how much time we left, right? If we want to finish it, we'll make it done, okay? But we'll force the use to 1. If it's now, we'll force to 0 and pay for the user. And for the time sensitive one, so the time sensitive jobs, first one is the shutdown marks for defined training completion. So if you're running, there must be a completion. The second one, it says, okay, for the cumulative of time, okay, it must equals to the job. To the job time, the task time that we use. Okay, the task time is computed by the equation we used before, and if it's 0, it says we don't run the instance in the node. Okay, the third constraint says, okay, if it started, you cannot stop. You cannot stop until you finish it. The fourth one says, okay, once I finish it, it will mark as done. It's a completion of the work. And this one is the representation of those equations. The fourth one is the non-time sensitive job here. It's basically the same. The only difference is the time frame. The time frame changed from the user defined time to the total time frame because it's time insensitive jobs. Then comes the transfer for the transfer jobs. So how do you define transfer? If this transfer job, it must be done. It must be still completion. So we'll go first one. We'll go through all the job of the completion. But then we will go through the nodes that the user upload. The user upload will go through the node that at the node that in the location I, right? Basically, if the user upload the jobs in the location 1, okay. If the completion is not made in the location 1, then we'll consider it a transfer because it finished in the other somewhere else. If this task is transferred, the training data need to upload or download into another location. This one says that D stands for the data size of the training data. Okay, and if it is time sensitive, you need to transmit the data before the due time. If it's not, it's in the time frame. Okay. And this one goes to say it's basically upload a job tasks or the model. There's upper bound for data transmission because we have limited bandwidth. You cannot transmit 1 terabyte in a second, right? So this is the range in time t. Okay, so this one illustrates that. Okay, we'll check all other nodes besides the location that user upload the project, upload the tasks. Then comes the transfer jobs. So after we send it out, okay, those are the 4 jobs we transferred out, right? There must be some download, right? So to a location. The first one says, okay, once it transfer out, it must receive by a node from other location. For the second, third, and fourth, it tells you the upload bound, the download bandwidth of the nodes and the data center in a whole. Okay, so you cannot download 1 terabyte in a second. That's yeah. The third one then is the third part of the transfer jobs. Okay, once it says transfer, okay, we will set a bar, right? We'll set a bar. For the startup. Basically, it says what we will accumulate. We will do a sum that's to get the accumulation of the data we received. If the data we receive is smaller than the total data, okay, because of these 2 constraints, the only state we can use is 0, which means you cannot start. Once we receive everything at t in t plus 1, we can either choose start or not start. We have options to choose start or not start. Okay. And with these constraints we talked above, it ensures that the LM test only transmit to a single node, and it won't start until the total job is transmitted. And for these are the computer node energy modeling. For the computer nodes, we set it into two modes. First one is the idle mode, which means it's just doing nothing, wait for a job. The second one is once we receive the jobs, we will have this is the rated power. This is the coefficient of the jobs. That is called TDP, which tells how much percent of the computing node we want to use. Okay, and then those are the constraints to tell whether the node is turned on or turned off. Once it's fully turned off, it consumes no power. If it's in an idle, it consumes low level of energy, and if it's working, it consumes a lot of energy. And this is a table of the performance, the power performance specification of all kinds of nodes here. So we made a modification in work 3, which is the temperature controlling. And temperature controlling, we in the previous work we think this one is constant, and now it's not constant anymore. It will, for this one, we think most of the energy consumption in the local node convert the electricity into heat. But you can add a coefficient to that, either 30% or 80% or 100%. It's up to the user. The heat in the data center needs to be removed and make it to the atmosphere, right? And we use the because also we divided our data center into different zones. Those zones we use the RC mode to mimic the temperature or heat exchange in different zones. And this detail can be found in this paper. Okay, then we applied our hybrid compatible nonlinear implementation approach. Since you already observed that in the object function, there are nonlinear parts, right? And we have it's a bilinear part. So, but thanks to the we use the quantum unconstrained binary optimizations to reformulate the object functions, because because it's x times q times x, right? So we can this one can be x1 and x2, x3 and x4. It can be different, and then we plug into our previous algorithms. Then we can let it run. Okay, so this is the simulation result. We can see that those drops they are well arranged. They are well arranged, and for TJP3, which is the time sensitive, it was transferred. It was transferred to from data center 1 to data center 2. Okay, now you can see the temperature and barrier chart. The temperature goes down goes down to the in the range of the acceptable temperature zones, and this is the node. Once it finishes this one, it completely turns out of itself. Okay, then we applied our Benders compositions, and so this one you can see that it converges, it's good, and for the final numbers, it matches. Because the D-Wave close is public access to the public access of its quantum annealer, so therefore we use the OpenGIJ and the bifurcation as the computing platform, which is the local, and we tested the local sober access time. For the GIJ, it consumes about 114. Sometimes it will take 4 iterations because it cannot guarantee every time we give the optimal solution to generate the cuts. For the simulated bifurcation, I think this one is most powerful. It's slightly powerful. It's slightly more powerful than the GIJ because this one used the GPU. This one used the CPUs. And for this one, if we use this method, these keywords, then give you about 23 seconds per iterations. So we can see that GPU runs faster than CPU-based algorithm, simulated quantum annealing algorithms. And for those two techniques, you can refer to this paper and this website. It has detailed detailed model and math behind it, but they all do simulated quantum annealing. Okay, then talk about the future works. In the future works, we can do a lot of decorations or a lot of extension on it. First one is we want to do different kind of bundle computation, because other than the classical bundle computation, we have a lot other kinds of bundle computation, either the bundle store computation, the general bundle computation, large bundle computation. They have different kinds of master problems that we need to reformulate it. And the second one is the high order unconstrained matter optimization. Okay, so for this one, for the one we use is the quadratic unconstrained matter optimization. This one is the second order, right? For high, we can make it to the third or fourth order, but we need to decomposition. So we want to find a method that change those things into a quadratic binary, to a quadratic unconstrained binary optimizations. Then we can apply the quantum annealing. Or if we use the digital quantum computing, okay, the ghost gates, we can achieve the high order unconstrained binary optimizations by doing circuit, because for those gates, they can connect multiple qubits in one operation, right? We don't, in that way, we don't need to do the computations. But however, the concern is that you need to build a circuit by yourself. That is the challenge that we're facing. But I've already seen some researchers has working on this one. Okay, for in the mode wise, we can upgrade our modes. First one, we can do unit commitment. For example, inside the data center generators, we want to use the unit commitment to the compensation of the energies, right? Sometimes the electricity is too high, we can use our own generators to generate power to meet the demand. In the unit commitment, it has convex constraints. It's called the mixed integer second order cone problems, which looks like this. Okay, we can by finding this one, we can use either Bender-Stowe or general bundles to solve this kind of problems and get solutions. And the second plugin we can do is the dynamic flex training task scheduling. So we can add some uncertainty of the in the problems to see, okay, if this job training could be longer or shorter or something like that. Add some uncertainty to the models to see how quantum computing performs. The third one is quantum communications. Right now, there already have some papers that could talking about quantum communication, because I believe Dr. Han already noted, right? Now you have the quantum communication between satellites or some between the land, because the Earth and satellites, right? So in the future, probably we can use the quantum communication to transfer the data or to do the job scheduling or something like that, and to make our model fruitful. Okay. So in conclusion, the quantum computing provides a special way to deal with the complex mixed integer programming by leverage both quantum computing and classical computation power. Our HQC band can reduce the computation time for mixed integer programming significantly. So in work one, we formulated the math problems of the bundle optimizations and validated algorithms. And then we introduced the Python package by implementing the HQC band problems. In the second work, we validate our algorithms by a model, which is energy management in the internet data centers, and we we drew the conclusion that our approach outperforms the classical boundary condition approach in practice. In the work 3, we extend our model to internet data centers. Then we add job scheduling, and we add nonlinear elements in our model. Okay, we can see our HQCM method is feasible for solving certain MI-NLPs. Okay, so these are my publications that are already published or are ongoing. Okay, so should you prove or still prove my defense? Okay, thank you.